Okay, so in this chapter, we'll define a new quantity called linear momentum. Okay? And again, when you define a new quantity, you do it because it's useful. Okay? And the past quantities that you've defined are not sufficient to do the job. Okay? So let me briefly tell you the use of this quantity. Okay, so linear momentum is a vector quantity. It's denoted by P. And for a particle, it's the mass times the velocity of the particle. Okay? So that's the linear momentum of an object. So if that's the velocity and that's the mass, that's the linear momentum is P is mass times velocity. Okay. Now, if you have several particles, you can define the linear momentum of the system. Since these are vector quantities and you know how to add vectors, you define the linear momentum of particle 1, particle 2, particle 3, calculate the linear momentum of each particle and just add them up, and that's the linear momentum of the system. Okay. All right. Do you guys know Newton's second law? Do you guys remember Newton's second law? What?
Net force is equal to mass times acceleration.
All right. So you guys saw Newton's second law was force equal to mass times acceleration. If a force F acts on an object, that is equal to the acceleration of the object is force divided by the mass of the object. Okay? The acceleration of the object is the force divided by the mass. Okay, well, actually, Newton's second law, the more precise form of Newton's second law is this. The force acting on an object is equal to the time rate of change of its linear momentum. Okay. Well, let's put the definition of linear momentum in there. Oops. All right, so if this is the more correct form of Newton's second law, why do you keep hearing this as Newton's second law? Okay, so we'll show you why they always introduce this as Newton's second law. Okay, so here's the correct form of Newton's second law. Force is time rate of change of momentum, linear momentum. This is d by dt of that. Okay, and now you can think of these. We'll use the chain rule. This you can think of this as product of two functions, dm by dt times velocity plus m times dv by dt. All right, that is equal to dm by dt times velocity plus, what is dv by dt? What is dv by dt?
Instantaneous
Acceleration, that's acceleration. So m times a. Okay, so that was that term. So the real form of Newton's second law, the correct form, has this extra term. So why do they leave this out? Till now you've heard this form as Newton's second law.
is constant. One of them is constant. That's
What is constant?
the acceleration. Or not the acceleration.
Well, I see this equation says this equal to this times that. Nothing has to be constant.
Oh, I was answering the part where you said that it wasn't normally in there.
Yeah, this wasn't normally in there.
Yeah.
So why is that not there?
Mass is a scalar. Therefore, the derivative of scalar is 0. So it'd be 0 times velocity.
No, my mass can change. If I lose weight, my mass changes. It's still a scalar. See, my mass just changed. All right, so the reason is in most situations that you encounter when you get in your car weighs 3,000 pounds, you drive 100 miles, and you used up 1 pound of gasoline. Your mass hardly changes. So in most of our situations, dm by dt is 0. And so that's why we don't have to account for that. Okay, so that's why, and when in high school it's introduced, you haven't done calculus yet, so in most 99% of the situation, F equal to ma is good enough. Now, if on the other hand, if you're Elon Musk, your mass changes tremendously. Within a few minutes, you've lost 90% of your mass in a rocket. Okay, so this is Newton's second law. All right, so that's why we are introducing linear momentum, because it'll be useful in several situations. Okay. Now here's another thing that you can handle. All right, so we learned. You guys remember from one of the previous chapters, how do I change the energy of this object? I can do work on the object and increase its energy. If I do negative work on the object, I can decrease its energy. Okay. You saw that last time, and you learned how to calculate the work done by a varying force on an object as it moves. Okay, x1, x2, as its location changes. So you saw that if you plot the x component of the force as a function of position. Okay. So here was a force that was changing with the spatial coordinate. Okay. And you saw that, last time you saw that the area under this curve, what is that equal to?
The antiderivative, or the integral of the function?
Yeah, what is that equal to? That's equal to the work done by that force. Okay? You saw that. And that, if that was the only force acting on the object, that shows up as the change in kinetic energy of the object. Okay, so that was the work energy theorem. Okay. Now that you're learning about linear momentum, what you learn to do is handle situations like this. So this was a force that was changing with position. Now you learn how to deal with forces that change with time. Okay? So let's say you have a force like this. Okay? This area we'll call it an impulse. And that'll be just like this. Okay, the work done was equal to, shows up as change in kinetic energy. This impulse will equal change in linear momentum. Okay. So now that you learn about linear momentum, you will be able to handle forces that change in time. Okay. So you've learned how to handle forces that change with spatial coordinates. You'll learn how to handle forces that change with time. Can you think of a situation where forces change with time? When do you encounter such situations? I mean, when we do something, we're doing it for a good reason. So when do you encounter these situations? Every time you play a sport, okay, let's say this is golf. I didn't want to draw soccer because I can't draw good. All right, so when the club comes in contact with the ball, it exerts a force. Okay, so before the club is in contact with the ball, the force the club exerts on the ball is 0, and then this force, as the club compresses, the force gets larger and larger. Okay, And in many situations, this force can be as large as 3,000 times the weight of the ball. Okay? So here's a situation where the force is lasting maybe about 100 milliseconds. It can be quite large. Okay? And in situations like this, you don't even want to think about calculating the acceleration, okay, the instantaneous acceleration. It doesn't do anything for you. Okay? What will be most relevant for you is what is the area under this curve and what is the effect of that area. And the effect of this area is the change in momentum of the object. Okay? All right, so those are some of the things we'll learn in this chapter. Okay? So the hero of this chapter is linear momentum. Okay, so this is a new quantity we are defining. It's a vector quantity, and that's the mass of the object times the velocity of the object. Okay. All right, so let's get into the chapter. And so here's a fairly neat thing. Okay. So you guys have all played pool. Okay. So I'm going to show you this guy breaking the rack. And what we'll do is we'll make a comment about, so the cue ball hits the rack, and before any ball collides with any of the sidings. So the collision will be fairly complicated, but we will be able to say something neat about this collision. Okay, so let's see this. This will last less than half a second. So what we are going to say is, so I'm going to draw a side view. So here's the cue ball. You shot the cue ball, there's the rack, and the cue ball has collided, and the racks and all these balls have gone helter-skelter. Okay. Now, this was an elastic collision, and when you play cue balls, that's an elastic collision. So kinetic energy initial was equal to kinetic energy final. The sum of all the kinetic energies of these guys is equal to the kinetic energy of this cue ball. Okay, these guys were all at rest. Now, here's another thing you can say. You can calculate the final momentum of all the balls and the initial momentum of the system. And you will learn that this is also true. So here are two conserved quantities. Okay, so that's a powerful statement. Here's after the explosion. This seems quite a complicated situation, but here are two beautiful things that you can say. Momentum was conserved and energy was conserved. Okay? All right. So linear momentum, and now you see why we'll be talking about collisions. You'll learn that in collisions, momentum will be conserved. Okay. All right, so linear momentum, collisions, and impulse. This word impulse is that guy. So when we learn how to handle, when we look at forces that vary with time, the area under this curve, that's called impulse. This area is called an impulse. Yeah. And the impulse acting on an object changes its momentum. Yeah. All right. So we'll learn about linear momentum. Linear momentum is denoted by P. In this chapter, we define another conserved quantity. What do we mean by conserved? That quantity is constant throughout the evolution of a system. Okay? And you'll learn that that is true when there's no external force acting on the system. Okay. So we'll learn about this conserved quantity, linear momentum, which will put an additional constraint on how the system evolves in time. What does that mean? Puts an additional constraint. Okay, so what we saw was, so in this breaking up of the pool rack, this is not a random process. It has to satisfy this condition and it has to satisfy this condition. Okay, so it's, even though there are infinite possibilities, it's still not totally random. Okay, so this, after the collision, these particles have to move such that they satisfy these two constraints. Okay? So that's what that means. Okay. So the quantity momentum is just as powerful, important, and useful as energy. You always hear of conservation of energy, but momentum is just as useful. Okay? And that's what they're showing in this diagram. So here's this guy colliding with him. This guy's going in that direction. This guy was going in that direction. They collide, and after the collision, this guy is deflected off in this direction. This guy is deflected off in this direction. Okay, so this guy's initial momentum is that. This guy's initial momentum is that. The total momentum of the system is this vector plus this vector, which is that. After the collision, this guy goes off like that. There's his final momentum. This guy's momentum is that, and the sum of these two is like that. Okay, so in this collisions, the constraint is that momentum has to be conserved. The total momentum has to be conserved. Okay. So that's what's shown there. So again, when the applied force varies with time, it's more convenient to deal with linear momentum. Okay. And we'll be dealing with forces that vary with time, and they're non-zero for extremely short intervals. Any sport you play, the forces you're applying are from 50 to 100 milliseconds. Okay. So to analyze such situations, you want to define linear momentum. Okay, so this collision will last probably about 100 milliseconds. Harder the ball, shorter the time period of the collision. Okay. So linear momentum is defined, that is mass times velocity. And here's the correct form of Newton's second law. The net force acting on a particle is equal to time rate of change of momentum of this particle. Okay. And this can be applied to a system as well. Net force acting on a system will equal time rate of change of momentum of the system. Okay. This is just some examples. Alpha particle is a helium nucleus. Okay, it's used in particle physics. Okay, and many radioactive substances. Everything above 82, atomic number 82, above lead, bismuth. You can see that on the periodic table. That's 82 is one of the last rows. They're all naturally radioactive, meaning their nuclei are unstable. Okay? And they're radioactive with various half-lives. Okay? So U-238, this isotope decays via spitting out an alpha particle, and there's the momentum of that. A 90 kg fastball, the momentum is about 10 kg meters per second. Okay. A charging rhinoceros, the momentum is 10,000 times more than that of a fastball. Well, why are we talking about the momentum? Why are we giving you these examples? All right, so what this means is, okay, so a fastball, a catcher stops the fastball in his mitt. That tells you, okay, so the time of, if you stop the ball in a certain amount of time, it tells you what kind of forces you have to apply. Okay, so if you try and stop a rhinoceros in the same amount of time, from this table you know you need a force 10,000 times greater. Okay, and so on. A super tanker, it's 1 billion times harder than stopping a fastball. Okay. All right, now as engineers, you'll be responsible for designing safety devices. Okay, so here is okay. So you can think of this as the force that you need to apply. Force is equal to change in momentum divided by time of change. Okay, so what does a safety device do? Okay, so we've talked about this example. You get on top of a building and jump off. If the sidewalk stops you, that's not a good thing. What would be a safety device in that case? Yeah. Yeah, so a bunch of mattresses, what they do is they slow you down over a longer time period, reducing the forces on you. Okay, so safety devices, that's their job. Okay. They reduce the forces on you. Smaller the force, smaller the acceleration. That's another way of saying it. Large accelerations are not good for your health. Okay. All right, so here's a guy going at 80 miles an hour. If the steering wheel stops him, very fast. Okay. And that'll exert a large force on you. In addition, large forces, so large forces, and then you got to deal with large pressure as well. For instance, if I push my thumb against my palm with a 10-pound force, that doesn't hurt. The same 10-pound force now with a pencil hurts. Okay. So you want to reduce the force and you want to spread it over a large area as well. Okay. So that's what this airbag does. Okay. All right. And so nowadays in cars and stuff like that, in addition to airbags, if you buy an expensive car, if you get into a head-on collision, the engine will drop and you have a crumple zone in the front. Okay, so your stopping time is increased tremendously that way. And a lot of the energy is dissipated in crumpling all the other stuff, so there's less energy to go into you. Yep. All right. So one of the things that's useful about linear momentum is in handling situations where the forces vary with time. Okay. So here's an example. All right. So let's see what this impulse approximation is. Okay. So here's the ball sitting on the tee. There's the force of gravity, there's the normal force, there's the friction force, okay, and that's the normal force, and the force applied by the club. Okay, so for a short amount of time, this force is much, much greater than any of these other forces. Okay, and so you can ignore all these forces. Again, this guy is canceling that guy anyway, and this guy is much larger than this guy. So anyway, so in many situations, this one force will be much greater than any of the other forces, and that's called the impulse approximation. Okay. And impulse is the area under that curve for this force. Okay. And so that's the only force we'll consider. Okay. All right, so here's Newton's second law. Force is equal to dP by dt. Here's an equation. When is that equation correct? When is it correct? At all times. I don't care how classically, I don't care how fast the force is changing. It's correct at all times. Okay, so this is an equation. And so, the neat thing about an equation is if you hit this guy with a hammer, you got to hit this guy with a hammer. All right, let's hit both of them with a hammer. What we're going to do is I'm going to integrate this with respect to time. Yep. T1 to T2. So here's T1 or T initial to T final. That's this area. Okay. And we'll give that area a symbol. We'll call it impulse I. Okay. And this guy, see, this is taking the antiderivative of a derivative. And you know from the fundamental theorem of calculus, that's just equal to momentum at the final instant minus momentum at the initial instant. Okay. So final momentum minus initial momentum. That is, this is the momentum of the object before the force came into play, and this was the momentum of the object after the force did its job. Okay. So impulse is equal to change in momentum. Impulse is written as I sometimes and J sometimes and all that. Okay. Okay, so probably your book has J, so I use J. Okay. All right, so greater the impulse, greater the change in momentum. Yep. So so here's a club hitting the ball. Okay, so the difference between, for instance, a professional golfer and me is their impulse has a much greater area, and the velocity of the ball off the tee comes out much faster. Okay. So if somebody can kick the ball further, what that means is their impulse is much greater. All right, oftentimes you're not able to measure this force in detail. We will do that in lab though. Okay, so that'll be your best experiment. So in lab, for instance, you will measure the force we exert 500 times a second. So that'll be the best experiment you'll do. But oftentimes we're not able to measure all of that, so all you care about is what is the average force you exerted. Okay. So how is the average force defined? Well, the force lasted that long. That's how long the force lived. Okay, we're going to make the average force also live the same length. What matters is the area. So the average force is defined as the average force which gives you the same area with the same length of time. Okay. So impulse is average force times the time over which the force lived. Okay. All right, you've always heard of conservation of energy, and now we're going to introduce to you conservation of linear momentum. Okay, what do we mean by conservation laws? Here's some quantity that remains constant throughout a complicated process. Okay, so you saw that pool rack being broken. That was a fairly complicated process, and you learned what to say. You learned something to say. You learned that energy was constant, that you have learned a long time ago. But today, now we learn to say that momentum is constant also in that process. Okay? And that's what we mean by that. All right, so conservation of linear momentum. So here, and we already saw this diagram here, two pool balls colliding. Okay? And after the collision, this guy will deflect like that, and this guy will deflect like that, and that's what's shown here. And what we are saying is the total momentum before the collision is equal to the total momentum after the collision. Yeah? And the total momentum remains the same through the entire process. That's conservation of linear momentum. Yeah? And this is not to be taken lightly. For instance, in this room, there are billions and billions of collisions happening between the air molecules every second. And in every one of them, momentum is conserved. Yep. All right, so here's how you can say that. So you just saw that Newton's second law is the net force is equal to rate of change of momentum of the particle or the rate of change of momentum of the system. Okay. Now, the net force is internal forces. So for instance, when these guys, if there was an external force on this object, okay, so internal forces is when these guys collide. This guy will exert a force on him in this direction, and that guy will exert an equal and opposite force on him. Those are internal forces. Okay, so if this guy exerts a force on him like that, and this guy will exert an equal and opposite force. Okay, so the net force is any internal forces between the objects and external forces if there are any external forces acting on the system. Okay. Now the internal forces always cancel. So when you add them, they always add up to 0. So the net force is really any external force acting on the system. And if there is no external force acting on the system, this will be 0. dP by dt will be 0. That means P is constant, meaning P is constant, so P before the collision will equal P after the collision. So if external forces acting on the system are 0, that implies P is constant. Okay, and that's what you saw in the pool rack collision. Okay, there was no external force because, okay, so now I'll draw a side view. So here's the table. Here was the force of gravity, but that was being balanced by the normal force. Okay, so the net extra, and it was frictionless. Okay, so we were assuming that. So there was no external force on the system, and the momentum was conserved. Okay. So, for instance, in particle physics labs, they use this all the time. So here's a fella, and you can make these in particle physics labs. It's a neutral kaon, and let's say you make a bunch of these guys at rest. Okay, what is the momentum of these guys when they're at rest?
Constant?
A little more specific. What is the formula for the momentum? So if he's at rest, his velocity is 0, his momentum is 0. Okay, these guys might live about a billionth of a second. Okay, and then they decay. And this guy splits into these particle-antiparticle pair. Okay, now, so when this guy splits, his initial momentum was 0, and there's no external force acting on the system. The split is due to internal forces, and his final momentum has to be 0. This final momentum of this system has to be 0. Okay, so if these particle-antiparticle pairs are of equal masses, they fly apart with exactly equal speeds. Okay, so this guy will split into 2 pieces, and the 2 pieces have to fly exactly 180 degree apart and exactly at the same speed. Okay, now they can fly apart in many directions, but you can say that here's something we can say: the angle between them is exactly 180 degrees, and their speeds are exactly the same. Okay, so that's the power of this thing. All right, now we'll apply these concepts that we've learned to we'll use linear momentum in studying collisions and explosions and stuff like that. Okay. If after the collision the kinetic energy is the same as the initial kinetic energy, that's an elastic collision. Okay. And when you play pool, that's an elastic collision. And so, for instance, okay. So here's a cue ball, and you can hit a straight shot, and if it's an elastic collision, if this is going at 5 meters per second, in the cue ball will come to rest, and this guy will go at 5 meters per second for a head-on collision. Okay, so that's an elastic collision. The kinetic energy after the collision is equal to the kinetic energy before the collision. If the final kinetic energy is less, then it's an inelastic collision. Okay, less or more, it's an inelastic collision, but generally this is what we see. Okay, so what happened to the kinetic energy then? Was energy lost? Energy is never lost. It got converted to some other form of energy. So sound, heat, and stuff like that. Okay, so that's an inelastic collision. So for instance, you can take two, instead of pool balls, you can take two balls of pizza dough, and collide, throw them at each other, and they'll come to rest. So all that kinetic energy is lost. If the final kinetic energy is zero, then the collision is perfectly inelastic. So you take two pizza doughs and throw them at each other, okay, and they'll come to rest, assuming they're the same mass and they started off with the same speed, because they'll come to rest, and all that's a perfectly inelastic collision. Okay. If the final kinetic energy is greater than the initial kinetic energy was released, and that was due to an explosion. Okay, some chemical energy was converted into mechanical energy. All right, so elastic collisions are where kinetic energy and momentum are conserved. Okay, so we are dealing with situations where the external force is zero, and elastic collisions are, so now that you've learned about momentum, okay, so you can say two things about collisions. Okay, so in an elastic collision, kinetic energy is conserved and momentum is conserved. Okay. In an inelastic collision, kinetic energy is not conserved. Okay, so it's most of the time it's reduced, but sometimes it's increased as well. So that's an inelastic collision. But momentum is conserved. Okay, so as far as collisions go, this is a more powerful quantity. Okay. Kinetic energy is energy comes in so many different forms that the sum total of all different forms of energy is conserved. You can't keep track of just kinetic energy. You can't keep track of all forms of energy. It's hard. So momentum is more useful. So momentum after the collision is equal to momentum before collision. Okay? So in an inelastic collision, okay, this is what you got to rely on. In an elastic collision, you can use both these guys to solve problems. Okay. In an inelastic collision, only this guy is what you can rely on. Okay, so here's an inelastic collision. So here are two objects, they're heading toward each other, and they stick together. If they stick together, now you can precisely calculate the final velocity. And again, we're doing this in one dimension, to keep things simple, and then we'll graduate to 2 and 3 dimensions. Okay. So right now we're doing in one dimension. So all these objects are moving in a straight line. Okay. And that's what we'll do in labs as well. Okay. So these two guys collide. After they stick together, you can precisely calculate this final velocity. Okay. So here is the initial momentum of the system, m1 v1 initial plus m2 v2 initial. They have stuck together. Now that's the total mass, and that's the final velocity. So the final velocity is initial momentum divided by that. Okay, so if the two objects stick together, they have to go with that speed after the collision. It doesn't matter what the pizza dough is made out of. If they stick together, that's the precise velocity it has got to go through. Yep. So you can, so imagine this. You can make two steel balls, put Velcro on top of them, and they'll stick, and that's the velocity they'll go with. Or you can have two pizza doughs, they'll stick, and that's the velocity they have to go with. Okay. What is an elastic collision? Well, momentum is always conserved. Elastic collision is where kinetic energy is also conserved. This particular kind of energy is conserved as well. So if these two, again, we're considering one-dimensional case. So these two guys collide, and after the collision, they bounce off. If kinetic energy is conserved, they can't stick together, because then kinetic energy would not be conserved. Okay. So here is the initial momentum for the system is equal to the final momentum. That's that statement. Okay. And here is the initial kinetic energy equal to final kinetic energy. Okay. That statement. Initial kinetic energy equal to final kinetic energy. Now, so in one dimensions here are two equations, and you can solve for two unknowns. Okay. But it turns out that with a little algebraic manipulation, see, this is a quadratic equation in velocity. You can reduce this to two linear equations. Okay, so if it's an elastic 1D collision, here's the momentum conservation, and this reduces to, see, this is relative velocity. This is V1 initial minus V2 initial equal to V1 final minus V2 final with a negative sign. Okay, so what that means is, okay, so let's say, and you've seen this in pool tables. Okay, so here's a cue ball coming at an object ball. Let's say this is coming at 5 meters per second. V1, so this is ball 1, and that's ball 2. V1 minus V2, that's 5 minus 0.5 meters per second. Okay. And after the collision, what happens is, this guy has to go off at 5 meters per second. Okay. This would be 0. Okay. And V2 final is 5 meters per second, so it would be minus of 0 minus 5, which is 5 meters per second. So if it's an elastic collision, okay, this guy moves off at 5 meters per second. Okay. So if you're sitting on ball 2, before the collision, the ball 1 is coming at you, and after the collision, the ball 2 is going away from you. Okay? At the same speed. So that's what this statement is. All right, so again, this holds only for an elastic collision in 1D. Okay, so now we'll consider the more complicated case, a 2D collision. Okay, so you saw that momentum, which is a vector quantity, is conserved. So if you're considering a 2D case, so that's what happens on a pool table. Things are moving in 2 dimensions. Okay? So the y component and the x component independently must be satisfied. Okay, so the x component of the momenta and the y component of the momenta should equal the same quantities before and after the collision. Okay? So for instance, here's a glancing collision. This object strikes that object, and after the collision, the blue ball goes off in this direction, the orange ball goes off in this direction. Okay, so the initial momentum was only in the x direction. Okay, this guy was 0. So after the collision, they must go off such that this y component cancels that y component, and this x component plus this x component should equal that x component of the momentum. Okay. It turns out that so you can prove this. If the two masses are equal and the collision is elastic, do you guys know what is the angle between these two guys? I'm sorry? It'll be 90 degrees. Okay? Well, even though you couldn't state it, you knew it because you've all played pool and you aimed it that way. Okay, so again, if it's an elastic collision and if the two masses are equal, after the collision, that'll be 90 degrees. So that's how you're hardwired. So if you want to beat a world champion, how do you do that? You can beat a world champion. Here's how you do it. You have 2 cue balls, one a regular one and one with a different mass. Have him play with a different mass, him or her. No. So, of course, he'll know instantly, but, All right. Now we'll talk about something called a center of mass. Okay, so when I toss this object, what is its trajectory? What is that trajectory?
Parabola?
It's a parabola. Okay. Now, if I toss this pencil, okay, what is the trajectory of that pencil? Okay, let me do it again. What's the trajectory of that pencil? Okay, so for an extended object, only one point went on a parabolic trajectory. And that point was the center of mass. No other point goes in a parabolic trajectory. Okay, and that's what this diagram is showing you. Okay, so only the center of mass goes on a parabolic trajectory. Every other point is a non-parabolic trajectory. So the center of mass, you can think of, if you turn that object into a point object, it would be at the center of mass. Okay, so if you wanted to squeeze that object into a point object, that's where you would squeeze it. Okay, so for extended object, the center of mass travels on a parabolic trajectory. So if you wanted to find the center of mass of object for, let's say, a 2-dimensional object, all you have to do is the following. Suspend it from 2 different points. So if you suspend this thing from there, the center of mass is below the point of suspension, somewhere there on that line. And to find exactly that point, suspend it from another point, it's on this line, and so the intersection of those 2 lines gives you the center of mass. And of course, if it's a 3-dimensional object, you just suspend it from 3 different points. Okay, so that's how you can find the center of mass. The center of mass of an object doesn't have to be within the object. Okay. So for these guys, there's the center of mass. So here's an interesting thing, which you may or may not know. I guess so. So, what is the motion of the Earth? What does the Earth do? It goes around what object? It goes around the sun. Well, actually, what is happening is, so there's the center of the sun. There's this. Now I'm talking about the solar system only with the Earth and the sun. Yeah. So there's the center of mass of the Sun-Earth system. So really, they're going around the center of mass. So the sun is making this circle, and the Earth is making that circle. So this is the center for both the circles. Okay. So think of this as a rod. This is the center of the sun. This is the center of the Earth. It's about this point that the spin is happening. Okay. Now, the thing is, this is about 100 million miles, and this is about 3 miles. So the sun is making a very small circle. Okay. And in fact, the sun is going at about 1 meter a second. So this is how fast the sun is going. How do we know? Well, that's what the theory tells, but you can actually measure it. Because if something comes towards you, the light appears bluer, and when it moves away from you, it's redshift. Okay. So in fact, that's how you can detect if, that's one way of detecting if planets have, if far off stars have planets around them. You keep absorbing their lights, that's one way of detecting it. If sometimes it's blue shifted and sometimes it's red shifted, then there's a planet. Now most of the detection is through occlusion, or so when the planet comes in front of the star, then the star dims, its brightness dims a little bit, and that's how most of the planets are detected. But anyway, so coming back to this, the center of mass does not have to be within the object. Okay, so, and you saw this last time when I showed you several demonstrations where the center of masses were outside the object. Okay. So if you have a system with a bunch of point particles, here's how you calculate the coordinates of the center of mass. The x coordinate would be each point particle, mass of each point particle times its x location divided by the total mass. Okay. Similarly, y center of mass is mi yi divided by m. Okay. Z is mi zi divided by total m. Okay. If you have a continuous distribution, this m gets changed to dm. So what you do is, if you have a continuous distribution, just break up the object into little chunks. Here's the mass of the little chunk, that's the mass of the little chunk. And then you do this three-dimensional integral. And of course, so for regularly shaped objects, the center of mass, for regularly shaped objects with uniform density, the center of mass is at the geometric center. Yeah. Anyway, so you would do that triple integral. So here was a fellow who knew his physics. Yeah. So here's an example of the center of mass. So where is your center of mass? Your center of mass is sort of behind your belly button. Okay. Now, most athletes have similar strengths and all that. What they can do is, so here's an athlete, here's a high jumper, and you jump and all that. And what you're able to do is you're able to raise your center of mass from this height to that height. And most athletes can do that. Okay? That's how much you can raise your center of mass. Okay. Now, in this old technique, so that's how high the center of mass went up. And that's what most people can do. Now, if you do the same jump like that, see, your center of mass is there. You raised your center of mass just like everybody else, the same height. But now you can put the bar at a higher height. So you can clear a higher jump. And that's how Mr. Fosbury won in 1968. He was the first one to do it in the Olympics in 1968. And he won by several inches. Okay, and now this has become standard technique for all high jumps and pole vaults and all that stuff. Yep. Okay, till now we've been applying all those equations just to a single particle, but they apply to a system of particles as well. So for instance, here's a bunch of particles going in that direction. You can calculate the total momentum of the system. It's just the vector sum of individual momenta. Okay? And the net force acting on the system is equal to, so this is the net force acting in the entire system, that's equal to rate of change of momentum of the entire system. Okay? So this equation applies to a single particle as well as to a system of particles. Okay? And when was this equation true? When is this equation true?
The mass isn't changing.
Very good, my friend. When the mass doesn't change, okay? And it turns out so here are three particles. Here's force 1 acting on this guy, force 2 acting on this guy, force 3 acting on this guy. There's the center of mass of the system. And this applies, again, when the mass is not changing, to a single particle as well as to a system of particles. Okay, the sum of these forces is the net force, and the center of mass will accelerate in that direction. So the net force on the system is the mass, total mass times the acceleration of the center of mass. Okay. And again, see, you guys know more physics than you think you know. See, you guys might have seen this. So when a firecracker is shot, or a shell is shot, and it explodes into a million pieces. Okay, before the explosion, it was going on a parabolic trajectory, the center of mass. After the explosion, the center of mass is still going on the same parabolic trajectory. Okay, so next time you watch firecrackers, when a rocket is shot, after the explosion, if you watch carefully, you can see the shell, empty shell, which has the most of the mass still. You can see its trajectory at night. Okay. Anyway, the center of mass is still going on that parabolic trajectory. All right, now we'll talk about rocket propulsion, which is based on conservation of linear momentum. Okay, so here's the deal. Okay, so I like to give this example. So let's say you're standing on a frozen lake, in the middle of a frozen lake, and you want to get to get to shore. What do? Well, if you have a physics textbook, what do you do? Okay, so your initial momentum was 0. If you have a physics book, you throw it in that direction, and then you will recoil in this direction. And if it's a frictionless surface, you'll get to the shore. What if you want to get there faster? Then you have to have 2 physics books. You throw the second book, and then you'll go faster. Okay, that's a rocket. All right, so the rocket initially was at rest, so we'll consider this, we'll imagine this happening in space. You shoot some hot gases, you recoil and go in that direction. Notice the total momentum of the entire thing is always 0. Okay. So you shoot some hot gases, you'll recoil. You want to go faster, you shoot some more hot gases. You keep shooting those hot gases, you'll keep going faster. Okay. The total momentum of the entire system is 0. Okay. So we'll introduce a couple of equations that are useful in rocket propulsion. Okay, so imagine this is happening in deep space. So here's this rocket that's flying. Okay. So here's the total mass of the rocket, and it's going at that speed. And now it wants to speed up. Okay, to speed up, what do you have to do? You have to spit something in the other direction. Or you have to shoot stuff in the other direction. Okay, so here was the situation, and so you fire a bit of hot gases and you speed up. So now this piece is going faster, and this piece is going in that direction. Okay. Okay, before I do this, let's do an example. You're going at 80 miles an hour, and then out the window you throw an apple at 10 miles an hour. Which way is the apple going?
Opposite to your movement?
I'm sorry?
Opposite to the direction of your movement?
Okay, so in the lab frame, the apple was, before you threw it, it was going at 80 miles an hour. And then you threw it at 10 miles an hour. So it's still going at 70 miles an hour in this direction. Okay? All right. Anyway, so here's this rocket. Now it's sped up, and this guy you shot in that direction. So the total momentum of this guy is equal to the total momentum here, because there's no external forces acting on the system. When you're spitting stuff out, those are all internal forces. Okay, and that's what this equation is saying. Here is the momentum initially, and there's the final momentum. This mass is reduced, okay, and there's the mass of the exhaust. Okay, this is the exhaust velocity, subscript E. Okay, so the faster the exhaust velocity, smaller this number, greater this number has to be. Okay, so if you want to pick up speed fast in a rocket, you want to have fast exhaust velocities. Okay. All right. And anyway, if you rearrange this, so there's the mass times, that's the change in velocity, is equal to exhaust velocity times how much exhaust you spit out. Okay. So you want a faster change, you want a faster exhaust velocity, and you want a higher burn rate. The faster you're burning fuel, the larger this number will be. Okay. So anyway, so here's in differential form mdv equal to v dm. Okay, and then you can rearrange that. So dm by m equal to what I'm, okay. Okay, and then we'll integrate both sides. Integral of this is, so from initial to final point, integral of this is so minus VE log M initial to final equal to V final minus V initial. Okay. Minus VE log M final minus and then we'll absorb this minus sign. This is okay. And this is equal to and that's what this equation tells you. So V final minus V initial, that's the final velocity of the rocket, minus the initial velocity of the rocket, is equal to the exhaust velocity times natural log of initial mass divided by final mass. What does this tell you? Initial mass minus final mass divided by final mass. What is the initial mass? The initial mass is rocket plus fuel, and final mass is just the rocket. Okay. So this equation tells you how, if you want to go that fast, how much fuel you need to carry. Okay. Now, of course, this is in space. Generally, we launch rockets from the ground, so we'll account for that in 1 second. Okay. But this equation tells you if you want to go that fast, how much fuel you need. For instance, to orbit Earth for lower orbits, you need a speed of 8 kilometers a second. Okay. So initial velocity will be 0, that will be final velocity. Now we'll put a term that accounts for gravity in a second. Okay. That will tell you that. All right, here's another equation we can come up with. So M, so this is that equation, M dV equal to that. M dV, again, these apply in deep space. Minus V d, okay, and then divide by dt. Okay, so that's mass times acceleration, and that's the thrust. Okay, that's the upward force that the rocket is exerting. That's the thrust, and it's equal to, we'll take, so the magnitude of the thrust is absolute value of the exhaust velocity times dm by dt. What is dm by dt?
Mass changing over time.
Yeah, mass of what? That's, you're right, that's the rate at which the mass of the rocket is changing. Why is the mass of the rocket changing?
Because of fuel.
Yes, so this tells you the burn rate, at what rate you're burning fuel. Okay, so your thrust depends on the exhaust velocity, that depends on the type of fuel you're burning, and you need greater thrust once you have chosen the fuel. That tells you how fast you have to burn your fuel. Okay. Now, for instance, so here's a rocket sitting on the launch pad. Okay. Now, if you want to take off, the thrust has to be greater than the weight of the rocket, otherwise you're not taking off. You know? Now, for most of the rockets, so for the space shuttle, the thrust was at launch pad, it was about 1.8 times the weight of the rocket. Okay, so you could take off. All right, now if you want to account for gravity, so okay, so here is Newton's second law. Okay, So change in momentum is force times the time over which that change happened. Okay, so what we'll do is, so to account for gravity now, so here is the mass of the rocket and its velocity is increased. Oops. So we'll consider two situations. Okay, and here it was m plus delta m, so the mass was greater and the velocity was lower. Okay, so here is the final momentum. So we're considering this rocket flying up. Here is the rocket small time later. Here was the rocket initially. Okay, so there is the, so, and remember you shot out some exhaust. Okay, so there's the total momentum, final momentum, minus initial momentum. That's the change in momentum. Final momentum minus initial momentum. And that's equal to the force. The force was the weight of the rocket times delta T. So here's an equation accounting for gravity, and you can rearrange all of that, and that's the equation you get. And again, just like last time, you can integrate, and here's what you get. Okay, so the final velocity minus initial velocity is exhaust velocity times log of mass initial divided by mass final minus g times that. Okay. So this equation just didn't have that g term. So in space, you didn't have that term. Okay. All right, so this tells you if you want to go at that speed, it tells you how much fuel you'll need. Okay. So those are the rocket equations. All right, I'll quickly give you a couple of numbers. Did you guys watch the video of the Starship launch? No? All right, I'm going to show you the video because it's an extremely important video to see. Okay. All right, so this thing was a pretty, anyway, the space shuttle, it took, so its orbital altitude was about 250 miles, 300 miles. Okay. So it took 8 minutes to go from here to orbit. Okay. It was going in at orbit, the speed was 8 kilometers a second from here to Ormond Beach. Okay. 8 minutes for the space shuttle to reach the speed of 8 kilometers a second, which is 8,000 kilometers per hour. The average acceleration was 15.8 meters per second squared. Remember, at launch, the thrust was about 1.8 mg, so at launch, the acceleration was 0.8 g. And what happens with a rocket? The thrust remains constant, you're burning at the same rate, but your mass is decreasing, so your acceleration is increasing. Okay, so as you're flying longer and longer, your acceleration is increasing. And peak acceleration was about 3g or something like that, further, okay? So the average acceleration was that. So when it's on the launch pad, it's heavy and you need a lot of thrust. So these guys were helping hands, the boosters. Okay? So when you're heavy, these are the three main engines. The fuel for these main engines was contained in there. And these are the solid rocket boosters. Okay. So at launch pad, it took off. These guys, all 5 engines were burning. These guys helped you along for 2 minutes, and then they were jettisoned. And then you were using the fuel there continued on for the next 6 minutes firing those rockets. I mean, firing using those engines. All right. So the space shuttle's 3 main engines and 2 solid rocket boosters, 3 main engines, generated about 8 million pounds of thrust, okay? Roughly 3.6 times 10 to the 6 kgs. And you see the mass was 2 million kgs. So that thrust to weight ratio is 3.55 divided by 2. Okay? So about 1.8. And that's sort of standard for most rockets. So you can check out the numbers for Falcon 9 and all that. Okay? The main exhaust was at 10,000 kilometers a second. So the hot gases coming out of the main exhaust were 10 kilometers. That's that velocity, the exhaust velocity. And at these exhausts, you're burning 12,000 kgs of fuel per second. This number corresponds to dm by dt. 12,000 kgs. 12,000 kgs is 12 small cars a second. You're burning up that much mass per second. The solid rocket boosters, they were burning 5 cars per second, okay, for 120 seconds, 2 minutes. Look at this, maximum power output of the shuttle's 3 space engines. Okay, by the way, here's this orange tank. There's the orange tank. Okay, and the fuel was liquid hydrogen. That's where the liquid hydrogen. Where does it say liquid hydrogen? Yeah, liquid hydrogen tank. So that was the fuel, and of course, to burn anything, you need oxygen. So there's liquid oxygen. Yeah. So that's what this engine burned, and this was our solid fuel. Okay. The main engines which burned liquid hydrogen had a power equivalent of 20 Hoover dams. 40 million horsepower. Do you guys know how many horsepower your car has? How many horsepower?
400.
Huh?
400.
You so his car is being pulled by 400 horses. Yeah. What do you drive?
Big old truck.
A big old. Oh yeah. All right. So the shuttle only had 100,000 times the horsepower of your car did. Yeah. Look at these guys. There is the Starship. There is the thrust. 72,000 kilonewton, so 72 million Newton thrust. So the Starship could lift, well, so it can lift, a kilonewton is roughly your weight. So the Starship can lift up 100,000 people. That's what it can do. That's twice the thrust of the Saturn V rocket. Okay. All right, so we will stop here, but I want to show you the video before I give you a little break. All right, let's record the video. Why the heck? No. All right, so do you guys know, I mean, the deal with the rocket launch business? So these are just numbers for the Falcon 9. Falcon 9 is, okay, so again, if you want to go high up, the optimal strategy is you gotta have a multi-stage rocket. Okay. So the Falcon 9 here is the first stage, second stage. The first stage itself costs roughly $20 million. Yeah. You guys fly, right? You guys get on a plane? I mean, I can afford a plane ticket. Why can I afford a plane ticket? Because they keep reusing the plane all the time. Imagine if there was a plane, you use it one time and then throw it away. I couldn't fly. That's what we've been doing with rockets. You use it once 20 years ago, you use a rocket once and just throw it away. A $50 million object, one-time use. So, reusable is what you want to do. Okay, so this first stage is $20 million. To fuel it, it's only $200,000. Nothing. So you guys understand the need for reusability. And that's why now everything has become cheap. Now we can launch all kinds of stuff. So this guy, he's not really about going to Mars. He's just wanting to put an internet in the sky. He's going to take over the world. So the Falcon 9 can put up 16 of his Starlink satellites at a time. Starship can put up 64. This is a beautiful thing. Look at this thing. Okay, so you saw that this thing is what, I forget the dimensions of this, but anyway.
That's why I burnt all my shoes, and you should too. Let me explain. All my life I let my feet suffer.
3, 2, 1. We have liftoff.
What happened to sound?
Vehicles pitching downrange.
After engines.
So there's 32 Falcon Merlin rockets.
Coming up on hot stage separation confirmed.
See how fast this vehicle is moving on the left hand. Landing burn.
13 engines.
Booster having burn shutdown.
Megadilla has popped the booster.
See that?
What an incredible deal!
That's $100 million snatched out of the sky.